Dust drifts silently through the darkness of space tonight. Tiny grains, smaller than particles of smoke, float endlessly. These specks seem insignificant when you first think about them. But they built everything we see in the universe. Every star, every planet, every living thing on Earth. All came from dust floating in the emptiness between stars. Tonight we follow dust on its cosmic journey slowly, from the death of the first stars outward through space, through cold clouds where new stars are being born, into swirling disks where planets take their first shape. We'll see how dust builds worlds over millions of years, how it carries the ingredients for life across vast distances, how it shapes galaxies and organizes their beautiful spiral patterns. This is not a story about grand explosions or violence. It's about the quiet, patient work of the smallest things, building the largest structures one grain at a time steadily. So settle in and breathe slowly as we begin. This journey through the universe's most humble yet powerful builder, the cosmic dust that connects everything together across time and space. In the beginning, there were no dust grains anywhere at all. The early universe contained only hydrogen and helium gas floating freely. These were the simplest elements created in the Big Bang's first moments. For hundreds of millions of years, only these gases existed throughout space. The universe was simple, pure, and waiting for something to change it. That change came when the very first stars ignited their nuclear fires. These first stars were giants unlike any stars we see today. They contained only hydrogen and helium without any heavier elements present. This made them burn incredibly hot and bright compared to modern stars. They lived fast and died young, exhausting their fuel in just millions of years instead of billions, like our sun will eventually do. When their fuel ran out, these massive stars collapsed catastrophically and violently. The collapse triggered supernova explosions that tore the stars completely apart forever. Inside these dying stars, something remarkable had happened during their short lives. Nuclear fusion in their cores had created new elements never before existing. Carbon formed from fusing helium nuclei together in the star's center. Oxygen formed from fusing carbon with helium in deeper burning layers. Silicon, iron, and dozens of other elements formed in the final moments. These elements were locked inside the stars until the supernovae released them. The explosions scattered these new elements across vast regions of space surrounding. As the hot gas from the explosion expanded outward rapidly into space, it began to cool down gradually over thousands of years of expansion. When the temperature dropped low enough for atoms to stick together finally, the very first dust grains condensed from the cooling gas like dew. These primordial dust grains were microscopic, far smaller than anything visible. Each grain was just a few atoms across, incredibly tiny and delicate. But they were something entirely new in the universe's chemical composition completely. These first dust grains were made of carbon, silicon, and oxygen primarily. Carbon formed into tiny graphite flakes and diamond crystals, microscopically small. Silicon and oxygen combined to form silicate minerals like tiny glass beads. iron condensed into metallic grains with magnetic properties that affected their motion. Each type of dust grain had different properties affecting how it behaved. But all of them shared one crucial characteristic that made them important. They were solid particles that could stick together when they collided gently. The dust grains scattered outward from the supernova remnant in all directions, carried by the expanding gas like seeds blown by cosmic winds. They drifted through the nearly empty space between other early stars, gradually spreading throughout the young galaxies that were just beginning to form. These dust grains were the universe's first solid matter existing anywhere. Everything before had been pure gas and plasma without any solids. The appearance of dust marked a fundamental transition in cosmic evolution completely. The dust grains began to affect their surroundings in important ways immediately. They absorbed starlight passing through the regions where they drifted slowly along. This absorption heated the dust grains to lukewarm temperatures above absolute zero. The warmed dust then re-radiated this energy as infrared light invisible to eyes. This process converted high-energy visible light into low-energy infrared radiation throughout regions. This cooling effect would have become crucial for future star formation to occur. More importantly, the dust grains provided surfaces where atoms could meet and bond. In pure gas, atoms rarely stick together because they're moving too fast. But on a cold dust grain surface, atoms can settle down temporarily. This allows them to find partners and form molecules more easily. The first molecules in the universe likely formed on dust grain surfaces. Hydrogen atoms meeting on dust grains combine to form molecular hydrogen gas. This molecular hydrogen would later become essential for forming new stars everywhere. The dust from these first stars was precious and rare initially. Each supernova produced only a tiny amount of dust grains total. Perhaps a few Earth masses of dust from each exploding star. Spread across light years of space, this dust was incredibly dilute and sparse. You could travel through these regions and rarely encounter a single grain. But over time, more stars formed, lived, and died in supernovae. Each explosion added more dust to the growing cosmic collection accumulating slowly. Generation after generation of stars enriched the universe with more dust steadily. Each new star that formed contained a tiny bit of dust from previous generations mixed into its hydrogen and helium gas composition. When these stars died, they created even more dust from their enriched material that contained more heavy elements than before had previously existed. This cycle of dust creation and recycling gradually increased dust abundance everywhere. Over billions of years, the universe became much dustier than it started. The first dust grains were also the first carriers of chemical complexity. Before dust, the universe was chemically simple with just 2 elements. After dust, dozens of elements were available throughout space for reactions. This chemical diversity would eventually enable much more complex chemistry to develop, including the organic chemistry that would someday lead to life emerging. The first dust grains were the ancestors of every complex molecule that would ever exist, including those in living cells billions of years later. These ancient dust grains also began to affect the light traveling through space. In regions where dust accumulated more densely than elsewhere in concentrations, Starlight passing through would be dimmed and reddened by the dust absorption. This created the first dark patches in the universe's otherwise bright appearance. These dark, dusty regions would become important for future star formation events, because darkness and cold are necessary conditions for gas to collapse gravitationally. The dust grains themselves were constantly being destroyed and recreated in cycles. Supernova shockwaves would vaporize existing dust back into gas atoms completely. But then new dust would condense again from the cooling gas afterward. Starlight would heat dust grains hot enough to evaporate them into gas. But in cooler regions, new dust would form again from that gas. This cycle of destruction and creation continued endlessly throughout cosmic time. Each cycle slightly changing the dust's composition toward heavier elements progressively over time. Some of the first dust grains survive to this day potentially, locked inside meteorites that have fallen to Earth from space above. Scientists have identified prosolar grains in meteorites through careful isotopic analysis. These grains have isotope ratios that couldn't form in our solar system. They must have formed in other stars before our sun existed. Some of these prosolar grains might be from the very first generation of stars that existed over 13 billion years ago, initially at the beginning. Holding these meteorite samples means holding pieces of those first stars directly. And the first dust grains that began building everything we see today. The first dust was humble in its appearance and amount initially. Just microscopic ashes from dying stars drifting through emptiness, seemingly lost. But these tiny grains carried the seeds of complexity and structure within. They would enable everything that came after to form and evolve. Without these first dust grains from the earliest stars that died, the universe would have remained forever simple and unable to build. The complex structures like galaxies, planets, and life that emerged later. The first dust was the beginning of everything solid and complex. The foundation upon which the entire cosmic architecture would be constructed. Over billions of years of patient accumulation and organization ongoing still today. Between the stars lies vast emptiness that seems completely devoid of anything. Space appears black and empty when we look up at night. But this emptiness is not truly empty at all when examined closely. Dust drifts through this darkness like snowflakes falling in slow motion, moving through the interstellar medium that fills the space between every star. This cosmic snowfall happens continuously throughout every galaxy in the universe today. The interstellar medium is the gas and dust filling the space between stars. It's incredibly diffuse, far emptier than any vacuum we can create on Earth. In the densest regions, there's about 1 atom per cubic centimeter of space. For comparison, Earth's atmosphere has billions of atoms per cubic centimeter, so interstellar space is almost perfectly empty by our everyday standards completely. But across the vast volumes between stars, even this thin material adds up. The interstellar medium contains as much mass as all the stars combined. Dust grains make up only about 1% of the interstellar medium's mass. The other 99% is gas, mostly hydrogen with some helium. But despite being such a small fraction of the total mass present, dust has an enormously disproportionate effect on what happens in space. Because dust grains are solid particles, while gas is just individual atoms. Dust can do things that gas cannot do alone by itself. The dust grains drift slowly through space, pushed by various forces acting on them. Starlight, hitting dust grains, exerts radiation pressure, pushing them away from stars. This pressure is tiny but acts continuously over long time periods. In intense starlight near hot stars, radiation pressure can push dust away, creating cleared regions around the brightest stars where dust is swept out. In dimmer regions between stars, radiation pressure is weaker and less effective, allowing dust to accumulate more easily over time in those locations. The dust grains also feel gravitational forces from nearby stars and gas clouds. Gravity pulls dust toward concentrations of mass slowly but steadily over time. In regions where gas has started to clump together under its own gravity, dust gets pulled along with the gas into the growing concentration there. This causes dust to accumulate in the same places where gas accumulates, making dusty regions even dustier over time through this positive feedback process. Magnetic fields threading through interstellar space also affect dust grain motion significantly. Many dust grains have magnetic properties because they contain iron and other metals. These magnetic dust grains align themselves with the interstellar magnetic field lines, and they can only move easily along the field lines, not across them. This makes dust motion anisotropic rather than isotropic in magnetic field presence. Dust can stream along field lines, but is trapped across them somewhat. The dust grains also collide with each other, occasionally, despite space's vast emptiness. When two dust grains collide gently at low relative velocity speeds, they can stick together through van der Waals forces attracting surfaces. This gradually builds larger and larger dust grains from smaller ones over time. Some dust grains in interstellar space are actually fluffy aggregates like snowflakes, made of many smaller grains loosely stuck together in delicate structures. These aggregate grains are fragile and easily broken apart by faster collisions. But faster collisions between dust grains can shatter them back into pieces. When collision velocity is high enough, grains break apart rather than sticking. This creates a balance between growth from gentle collisions and destruction from violent collisions that determines the typical dust grain size distribution observed today. Most interstellar dust grains are about 1/10 of a micron across, roughly 1,000th the width of a human hair for size comparison. As dust drifts through space, it gradually settles toward the galactic disk. Galaxies are disk-shaped with most stars and gas in a thin, flat plane. Dust drifts vertically through this disk, pulled by the disk's gravity downward. Over millions of years, dust that was high above the disk settles down into the disk, where it joins other dust already there accumulating. This creates a dust layer concentrated in the galactic plane clearly visible when we look at our Milky Way galaxy edge-on from our position. The dust layer in our galaxy is only about 200 light-years compared to the galaxy's disk, which is 2,000 light-years thick overall. So dust is concentrated in a thin layer 10 times thinner than the gas. This makes dust much more concentrated in the disk's midplane than elsewhere, creating the dark band we see when looking along the Milky Way at night. In molecular clouds, where gas is densest, dust also becomes very concentrated. These clouds are the densest regions of interstellar space found anywhere nearby. They contain thousands of atoms per cubic centimeter instead of just one. The increased gas density means increased dust density as well proportionally throughout. In the darkest parts of molecular clouds, dust becomes so dense it blocks all visible light from passing through these regions, completely creating darkness. This darkness is crucial for what happens next in these clouds eventually. The dust shields the interior of the cloud from starlight very effectively. Starlight contains ultraviolet radiation that heats gas and prevents it from collapsing. But dust absorbs this ultraviolet light before it penetrates deep into clouds. This allows the cloud's interior to become extremely cold, below 10 degrees above zero. At these frigid temperatures, gas loses pressure support against gravity's inward pull, and the cloud can begin to collapse under its own gravity to form stars. The dust grains themselves are also extremely cold in these dark clouds, typically only about 10 degrees above absolute zero temperature throughout the cloud. At these temperatures, atoms and molecules striking dust-grained surfaces stick firmly. Instead of bouncing off as they would at higher temperatures present elsewhere. This allows ice layers to build up on dust-grained surfaces slowly. Water ice, carbon dioxide ice, methane ice, and ammonia ice all accumulate, creating icy mantles surrounding the silicate or carbon cores of grains throughout. These icy dust grains are very different from bare dust grains found elsewhere. The ice makes them stickier, so they clump together more easily than bare grains. The ice also provides a surface where more complex molecules can form. Atoms landing on the ice can slide around until they find partners, then react to form molecules that couldn't form in the gas phase. Many organic molecules were first discovered on dust-grain ices in clouds. These molecules would later become important for life's chemistry developing on planets. The dust continues its slow drift through these clouds for millions of years, gradually accumulating in the densest regions where gravity is strongest, pulling it. Eventually, the dust concentration becomes high enough that grains start sticking together into larger clumps and aggregates that drift even more slowly through gas. These clumps can grow to millimeter sizes or even centimeters in special cases, becoming the first seeds of solid material that will build planets someday. But most dust doesn't immediately form planets after drifting into clouds initially. Most of it will drift back out into interstellar space again eventually. When stars form in the cloud, their radiation and winds push dust away. The dust gets scattered back into the general interstellar medium surrounding the cloud, where it resumes its slow drift through space, waiting for another cloud. This cycle can repeat many times over hundreds of millions of years. The same dust grains drifting in and out of clouds repeatedly throughout time. Some dust grains will be destroyed before they ever form planets anywhere. Supernova shockwaves overtaking them will vaporize them back into gas completely gone. Or they'll drift too close to a hot star and be evaporated away. But new dust forms continuously from dying stars to replace what's lost. So the cosmic snowfall continues unabated throughout the galaxy's life forever. New dust falling through space to replace old dust that was destroyed. An endless cycle of dust drifting through the quiet darkness between stars. Building up in some places, dispersing from others, always in slow motion. Like snowflakes falling in a cosmic winter that never ends completely ever. Molecular clouds are the largest structures made primarily of dust and gas. They span hundreds of light years across space and contain thousands of solar masses. These clouds are cold, dark, and incredibly dense by interstellar space standards. They're called molecular clouds because hydrogen gas inside them is in molecular form. Two hydrogen atoms bonded together as H2 molecules instead of single atoms. This molecular hydrogen can only form in regions where dust shields ultraviolet light. So molecular clouds and dust go together naturally in the same places. The clouds appear as dark patches against the bright background of stars behind. The Horsehead Nebula is a famous example visible from Earth with telescopes. It looks like a horse's head silhouetted against glowing gas behind it. The dark silhouette is actually a molecular cloud filled with dust blocking light. Thousands of similar dark clouds exist throughout our galaxy and every other. They mark the locations where dust has accumulated most densely over time. Inside these clouds, dust plays an essential role in cooling the gas down. When gas in space absorbs energy from starlight or cosmic rays passing through, it heats up and gains internal energy that creates pressure outward resisting. But gas can cool down by radiating that energy away as light again. In diffuse gas, atoms radiate by colliding with each other and emitting photons. But in dense clouds, radiation alone isn't efficient enough for rapid cooling. Dust provides an additional cooling mechanism that's much more efficient here. Gas atoms collide with cold dust grains and transfer their thermal energy. The dust grain heats up slightly from each collision, happening continuously around it. Then, the dust grain radiates this energy away as infrared light efficiently. This cools both the gas and dust, together maintaining low temperatures throughout. Without dust, molecular clouds would be much warmer and couldn't form stars. The low temperature maintained by dust cooling is crucial for gravity to win. Warm gas has high pressure that pushes outward against gravity's inward pull. Cold gas has low pressure that can't resist gravity as effectively as warm. When dust cools gas to 10 degrees above zero in cloud cores, the gas pressure drops so low that gravity becomes dominant over pressure. The cloud core begins to collapse inward under its own gravitational weight, finally. This collapse is the beginning of star formation happening right in these clouds. As the cloud core collapses, it fragments into many smaller pieces naturally. Each piece becomes a separate, collapsing region that will form one star eventually. The dust goes along with the gas as everything collapses inward together, concentrating into ever smaller volumes as collapse proceeds over time, progressing forward. The dust density increases as the volume shrinks from collapse's inward motion. During the collapse, the cloud core rotates slowly from its initial angular momentum. All clouds have some rotation from turbulent motions in the gas initially. As the cloud collapses and shrinks, conservation of angular momentum speeds rotation. Like a figure skater spinning faster when pulling arms inward from extension. The rotating collapse causes most matter to fall into a flattened disk, rather than directly onto the forming star at the very center point. The dust forms a disk around the forming star as collapse continues inward. This disk is dense, with dust and gas swirling around the central protostar. The disk is the birthplace of planets that will form later eventually. But first, the protostar must grow by accreting matter from the surrounding disk. Dust and gas spiral inward from the disk onto the growing protostar, adding mass until the protostar becomes massive enough to ignite fusion reactions. The dust in the disk shields the protostar from view during this stage. Looking from outside, we can't see the forming star at all directly, because dust absorbs all visible and ultraviolet light from the protostar completely. The dust heats up from absorbing the starlight and glows in infrared wavelengths. So we observe these forming stars as bright infrared sources without visible light, their presence revealed only by the warm dust surrounding them glowing brightly. Eventually, the protostar accumulates enough mass to start nuclear fusion in its core. Hydrogen begins fusing into helium, releasing tremendous energy that makes the star shine. The new star's radiation and wind begin to push against the surrounding material, creating an outflow that blows away some of the remaining dust and gas. This clears a cavity around the star, making it visible finally in light. The dust is pushed outward into the disk or blown away completely into space. But significant dust remains in the disk around the newly formed star still. This leftover dust is what will build planets over the coming millions of years through slow accumulation and growth from collisions happening repeatedly forward. The molecular cloud has done its job of bringing dust and gas together, creating conditions for a new star and planetary system to form successfully. The cloud eventually dissipates from stellar winds and radiation, pushing it away gradually. The stars that formed within it are now visible, no longer hidden by dust. But the dust hasn't disappeared. It's just changed location into disks around stars. Some stars form in small groups of just a few members together. Others form in giant clusters containing thousands of stars all at once. The Orion Nebula is an example of a giant star-forming region nearby. We can see it with the naked eye as a fuzzy patch in Orion's sword. Through telescopes, it reveals hundreds of young stars embedded in glowing gas and dust. The dust silhouettes show as dark patches against the bright, glowing background beautifully. Each dark patch might contain a forming star hidden inside its dusty cocoon. The molecular clouds are truly the cradles of star formation throughout every galaxy. Without these dusty clouds bringing material together and cooling it down efficiently, stars couldn't form as readily as they do throughout cosmic history observed. The dust makes the clouds dark, but that darkness is essential for creation. It provides the cold, shielded environment where gravity can finally overcome pressure and collapse the cloud into new stars that will light the galaxy. The dust clouds may be dark and seemingly lifeless initially to observers, but they're actually the most creative and generative places in the entire galaxy. where new stars are constantly being born from dust and gas accumulation, in a process that has continued for billions of years throughout time, and will continue for billions more into the future ahead of us. Around every newly formed star there exists a swirling disk of material. This protoplanetary disk is made of leftover gas and dust that didn't fall into the star during its formation process earlier when it was collapsing. The disk can extend outward for hundreds of astronomical units from the star's center. 1 astronomical unit is Earth's distance from the Sun for reference comparison. So these disks are incredibly large structures surrounding the infant stars present. The disk is thin and flat, like a pizza or record spinning slowly. Gravity has pulled everything toward the disk's midplane over time, flattening it. Material high above or below the plane falls down toward it, until everything settles into this thin, flat configuration stably maintained over time. The thickness of the disk is typically about 1/10 of its radius. So a disk extending 100 AU outward is about 10 AU thick. Dust makes up only about 1% of the disk's total mass initially. The rest is gas, mainly hydrogen and helium from the original cloud. But despite being a tiny fraction, dust is crucial for what happens next. The dust grains can stick together when they collide gently at low speeds. Gas atoms cannot stick together in the same way at all by themselves. So dust begins building solid structures while gas remains gaseous throughout initially. The dust grains in the disk orbit the star following Kepler's laws of motion. Inner regions orbit faster than outer regions around the central star's position. At Earth's distance, orbital period is 1 year by definition of our calendar. Closer in, periods are shorter, farther out. Periods are longer proportionally with distance. This differential rotation makes the disk shear, with inner parts moving faster. This shearing motion affects how dust grains interact with each other over time. The dust grains don't orbit in perfectly circular paths initially around the star. They have slightly elliptical orbits and are inclined to the midplane somewhat. This means their paths cross each other frequently as they orbit around. When paths cross, grains can collide with each other at relative velocities varying. Low-velocity collisions result in grains sticking together from surface forces attracting. High-velocity collisions result in grains bouncing off or shattering apart instead. The dust grains start small, about 1 micron in size initially present. That's about 1/100th the width of a human hair for comparison. But through gentle collisions, they grow larger over time through accumulation slowly. 2 1-micron grains stick together to make a 2-micron grain. 2 2-micron grains make a 4-micron grain when they stick together. This process continues exponentially, doubling size with each generation of sticking occurring. The growth is incredibly slow initially when grains are smallest in size. Because tiny grains have small collision cross-sections and collide rarely in space. But as grains grow larger, they sweep up smaller grains more efficiently. Their collision cross-section grows with size, making collisions more frequent over time. This accelerates growth once grains reach millimeter sizes and become larger. At millimeter sizes, dust grains are called pebbles by astronomers studying them. These pebbles orbit the star and continue growing by sweeping up smaller dust. They can grow to centimeter sizes and beyond through continued accumulation happening. At centimeter sizes, they become sensitive to gas drag forces significantly more. The gas in the disk orbits slightly slower than solid particles do, because gas feels pressure support that particles don't feel at all themselves. This creates a headwind that solid particles feel as they orbit through gas. The headwind causes solid particles to lose orbital energy and spiral inward slowly. This inward drift is faster for larger particles than smaller ones proportionally. Centimeter to meter sized objects drift inward the fastest of all size ranges. They can spiral from the outer disk to the star in just thousands of years unless something stops their inward migration effectively happening throughout time. This creates a potential problem for planet formation called radial drift barrier. If particles drift inward too fast, they'll fall into the star before growing, large enough to resist the drift through increased mass and gravity. This would prevent planets from ever forming at all in the disk. But observations show that planets do form commonly around most stars. So something must slow or stop the inward drift before particles are lost. Several mechanisms have been proposed to solve this radial drift problem existing. One solution involves dust concentrating into rings at specific locations in the disk, where pressure bumps or other features slow the gas's orbital motion locally, creating convergent zones where dust accumulates and drift stops temporarily there. These dust rings have been directly observed in many protoplanetary disks with telescopes. The ALMA telescope has imaged dozens of disks showing multiple concentric rings. These rings are exactly where we'd expect dust to concentrate and grow. Another solution involves particles growing extremely quickly through pebble accretion instead of slow. Large objects can gravitationally attract smaller pebbles, accreting them rapidly in accumulation. This can grow objects from centimeters to thousands of kilometers in timescales, much faster than previously thought possible through standard collisional growth alone happening. Pebble accretion might explain how planets form so quickly and commonly observed. Within the dust rings, particles continue colliding and sticking together steadily forward, growing to kilometer sizes called planetesimals by scientists studying planetary formation. Planetesimals are large enough that gravity becomes important for their behavior. They can gravitationally attract other planetesimals and smaller particles nearby effectively. This gravitational focusing enhances their growth rate beyond just collisions alone occurring. The planetesimals compete with each other for material in the ring. Some grow larger by winning the competition through fortunate early growth spurts. Others remain small and eventually get consumed by the growing winners. This creates a runaway growth process where the rich get richer over time. A few planetesimals grow much larger than average, becoming planetary embryos present. These embryos are Moon to Mars-sized objects dominating their orbital regions. The entire process from dust to planetesimals takes a few million years typically. This is fast by cosmic standards, but incredibly slow by human timescales. The disk must remain stable with gas and dust present for this entire time. If the gas disperses too quickly from stellar winds or radiation pressure, planet formation might be halted before completing successfully into full planets formed. Observations suggest disks survive for a few million years before dispersing away. The dust rings are beautifully visible in ALMA telescope images taken recently. These images show disks around stars light years away with incredible detail present. Bright rings where dust accumulates show up clearly against darker gaps between. The gaps might be cleared by forming planets sweeping up material in their orbits. Or they might represent regions where dust drifts through quickly without accumulating. Either way, the ring structures reveal the process of planet formation happening. Different rings at different distances from the star might form different types of planets. Inner rings inside the snowline where it's hot-form rocky planets. Outer rings beyond the snowline where it's cold-form icy and gas planets. The snowline is where water ice can condense on dust grains without evaporating. This typically occurs at a few AU from Sun-like stars in their disks. Inside the snowline, only rocky materials remain solid under the heat. Outside, ice triples the solid material available, helping planets grow larger there. The dust rings are the first architectural sketch of a solar system forming. They outline where planets will form and what composition they'll have. Rocky planets here, icy planets there, giant gas planets farther out still. This structure gets imprinted during the disk's early evolution from dust dynamics and determines the final layout of the planetary system that emerges. Our own solar system once had dust rings around the young sun. Those rings formed Earth, Mars, Jupiter, and all the other planets. We see these same structures now around other stars in their infancy, confirming that planet formation is a universal process throughout the galaxy. Dust rings are the cosmic blueprints from which worlds are drawn into being. After dust has grown into planetesimals, kilometers across in size fully, the process of planet formation enters a new and slower phase completely. Planetesimals must now collide and merge together to form planet embryos. These embryos are intermediate objects larger than planetesimals, but smaller than planets, typically ranging from moon-sized to Mars-sized in their total mass accumulated. This phase is called oligarchic growth by planetary scientists studying formation processes. Oligarchic growth means a few large embryos dominate each region of the disk. These embryos have grown large enough to gravitationally dominate their neighborhoods completely. They scatter smaller planetesimals into different orbits or accrete them directly onto themselves. The embryos grow by consuming the smaller planetesimals around them steadily over time, while preventing other embryos from invading their feeding zones effectively through dynamics. The growth rate slows down dramatically during this phase compared to earlier, when objects were small, collisions were frequent and growth was rapid. But as embryos grow large and clear out their zones of material, collisions become rarer because less material remains available to accrete onto them. An embryo might wait thousands of years between collisions with other large objects. This makes oligarchic growth take tens of millions of years, typically to complete. The embryo's orbits gradually become more circular and less inclined over time. Gravitational interactions with remaining gas in the disk damp their orbital eccentricities. Gas drag also circularizes orbits for objects that aren't too massive yet. This orbital damping keeps embryos in stable, non-crossing orbits for long periods, preventing them from colliding with each other, despite being in the same region. But eventually, the gas disk dissipates, completely blown away by stellar winds. When the gas disappears, the damping forces disappear with it entirely. The embryo's orbits are no longer damped and can become eccentric again. Gravitational perturbations between embryos can excite their orbits significantly over time. Eventually, orbits cross and embryos collide violently with each other in impacts. These giant impacts between embryos are dramatic and energetic events occurring suddenly. Two Mars-sized embryos colliding release tremendous energy instantly upon impact happening. The collision can shatter both objects or merge them into one larger body. The outcome depends on the impact angle and velocity at collision time. Head-on collisions at high speed tend to shatter objects into fragments. Glancing collisions at lower speed tend to result in mergers forming larger embryos. The merger process is messy and violent, not gentle at all during impact. The colliding embryos are partially molten from internal heat they've accumulated over time. The impact liquefies even more material from the tremendous shock heating produced. The two bodies splash together like drops of liquid colliding and merging. Material sprays outward from the impact site in a debris disk orbiting afterward. Some of this debris escapes into space, while some falls back onto the merged embryo or forms a satellite orbiting around it in orbit. Our moon likely formed from a giant impact during Earth's formation precisely. A Mars-sized embryo called Theia collided with the proto-Earth embryo long ago. The impact ejected material into orbit around Earth that coalesced into the moon. This giant impact hypothesis explains the moon's composition and orbital properties well. Similar impacts probably occurred throughout the solar system during its formation completely, creating the planets and moons we see today from the mergers of embryos. The giant impact phase is chaotic with orbits crossing unpredictably throughout. Embryos can be scattered into highly eccentric orbits by gravitational interactions happening. Some embryos might be ejected from the system entirely into interstellar space. Others might crash into the central star, ending their existence completely. The survivors grow larger through mergers, eventually becoming the planets we observe. This chaotic phase can last up to 100 million years, typically before settling. During this time, the system's architecture gets established through these interactions present. The final number of planets and their orbital spacings gets determined now. Systems with many giant impacts might end up with fewer, more massive planets. Systems with fewer impacts might retain more, smaller planets in their layouts. The randomness of impacts introduces diversity into planetary systems we observe today, explaining why every planetary system we've discovered is unique in some way. The embryos that survive and grow become terrestrial planets like Earth and Mars. In the inner solar system, where temperatures were high during formation time, only rocky materials remained solid to build planets from available materials present. This created small, dense, rocky planets close to the star's position centrally. in the outer solar system beyond the snowline, where ice remained solid. Embryos grew much larger by incorporating ice into their compositions, growing faster. These large icy embryos captured gas from the disk around them directly, growing into gas giant planets like Jupiter and Saturn seen today. Jupiter likely formed first among all the planets in our solar system originally. Its large mass gave it strong gravitational influence on the entire disk. Jupiter's gravity scattered planetesimals and embryos throughout the solar system dramatically. This sculpted the final architecture we see today with specific planet locations. Without Jupiter's influence, the solar system would look very different probably today. Perhaps with many more or fewer planets in different orbital arrangements instead. The embryo phase connects dust to planets through a series of growth stages, starting from microscopic grains through millimeter pebbles, kilometer planetesimals, ultimately reaching Moon to Mars-sized embryos, and finally to full-sized planets completing formation. Each stage involves different physical processes dominating the growth happening there. Dust sticks through surface forces, pebbles through aerodynamic drag effects present, planetesimals through collisional accretion, embryos through gravitational focusing and giant impacts. The final planets are the products of all these processes combined sequentially, taking tens to hundreds of millions of years to complete entirely throughout. The planet embryos represent a transitional stage between dust and worlds fully. They're too large to be just dust anymore, obviously in size, but not quite planets yet in their final form either completely. They're worlds in the making, still growing and evolving toward their final states. This stage is critical, but often overlooked in popular descriptions of formation. People think of dust forming planets directly and quickly, without intermediate steps. But the embryo phase is essential and takes significant time to complete. Understanding this phase helps us understand why planets look the way they do, and why planetary systems have the architectures we observe today around other stars. Dust does not exist in a permanent form throughout cosmic time at all. Dust grains are constantly being created, destroyed, and recreated in endless cycles. This recycling of dust through stars is crucial for enriching the universe chemically. Each cycle adds more heavy elements to the mix than before existed, eventually creating the chemical complexity necessary for life to emerge and flourish. When dust drifts into a forming star system, as we've discussed earlier, some of it gets incorporated into planets that form from the disk, but much of it falls into the star itself during the accretion process. Once inside the star, dust cannot remain as solid particles anymore. The temperatures inside stars are millions of degrees hot throughout their interiors. At these temperatures, dust vaporizes back into individual atoms instantly upon entry. The silicon, carbon, oxygen, and iron that made the dust grains separate completely. Each element becomes a gas of individual atoms mixed into the star's material. Inside the star's core, where temperatures reach millions of degrees continuously hot, nuclear fusion reactions transform elements into other elements over time progressively. Hydrogen fuses into helium in the star's core during its main lifetime. Helium later fuses into carbon and oxygen in more evolved stars burning. Carbon and oxygen can fuse into even heavier elements like neon and magnesium. This fusion process builds up heavier and heavier elements inside stars sequentially. Elements that didn't exist when the star first formed from its cloud. The original dust that fell into the star has been transformed completely now. Its atoms have been rearranged through nuclear reactions into new configurations. The silicon might have become iron through fusion reactions occurring in the core. The carbon might have fused into oxygen or neon in later stages. The star has become an alchemist, transforming elements through nuclear fire intensely, creating new chemical species that never existed in nature before fusion began. For most of a star's lifetime, these new elements remain locked inside it. The star's gravity is strong enough to hold everything in despite tremendous internal pressures from nuclear reactions trying to push outward against gravity's inward pull. But when the star's nuclear fuel runs out eventually at the end, the balance between pressure and gravity shifts dramatically and catastrophically happens. The star's core collapses while its outer layers explode outward in supernova. The supernova explosion ejects the star's outer layers into space at tremendous velocities. Material accelerates to thousands of kilometers per second from the explosion's energy released. This ejector contains all the new elements created by fusion during lifetime, along with even heavier elements created in the supernova explosion itself occurring. The explosion's extreme temperatures and neutron fluxes create elements like gold and platinum, elements that cannot form in normal stellar fusion at all during lifetime. All these elements get scattered across light years of space by the expanding ejector. As the ejector expands and cools down over thousands of years afterward, new dust grains condense from the gas just like after the first stars. But these new dust grains are chemically different from the original dust. They contain more heavy elements like carbon, oxygen, and silicon in them. They contain iron and other metals that formed in the star's core. This new dust is more chemically complex than the dust that fell in. The star has enriched the dust through its life cycle of fusion and explosion. This enriched dust now drifts through space like we discussed before earlier. It joins the interstellar medium mixing with gas and other dust present. Eventually it drifts into a new molecular cloud forming somewhere nearby in space. There it participates in forming a new generation of stars from the cloud. Some of this dust gets incorporated into the new stars when they form. And the cycle begins again with fusion transforming dust inside the stars. Each cycle through a star adds more heavy elements to the cosmic mix. The universe started with only hydrogen and helium after the Big Bang initially. Every heavier element has been created by stars through fusion and explosions. The carbon in your body was made in stars billions of years ago. The oxygen you breathe was made in stars and scattered by supernovae. The iron in your blood was forged in stellar cores and explosion shockwaves. Every element heavier than helium came from stars recycling material through them. This means dust is not just passive particles floating through space aimlessly. Dust is actively being processed and enriched by stars throughout cosmic time. Each generation of dust is more chemically complex than the previous one. This increasing complexity is what eventually enables life to form somewhere. Life requires complex chemistry with many different elements in combination together: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and many others in organisms. All these elements must be present in the environment for life to emerge. The first stars that formed could not have planets with life on them, because they contained only hydrogen and helium without other elements present. No carbon for organic molecules, no oxygen for water, no iron for metabolism. Those stars could form planets, but only gas giant planets without solid surfaces. Rocky planets, and life had to wait for later generations of stars. After enough stars had lived and died to enrich space with heavy elements. Our Sun is a third or later generation star formed from enriched material. The dust cloud it formed from contained about 2% heavy elements. This was enough to form rocky planets like Earth with diverse chemistries, and enough to eventually enable life to emerge on Earth's surface. We owe our existence to countless stars that lived and died before our Sun, each one recycling dust and adding more elements to the cosmic inventory. The recycling continues today throughout every galaxy we can observe in the universe. Stars are constantly forming from dust clouds, living their lives burning fusion fuel, then dying and returning enriched material back to space through winds and explosions. New clouds form from this enriched material and make new stars again. The cycle has continued for over 13 billion years since the first stars, and will continue for trillions more years into the future ahead. This cosmic recycling is essential for the universe's evolution toward complexity overall. Without it, the universe would remain forever simple with only hydrogen and helium. No stars could have planets. No planets could have life in them. The recycling through stars drives the universe toward ever-increasing chemical complexity, enabling new possibilities that didn't exist in earlier cosmic epochs at all. Dust is the vehicle for this recycling, carrying elements between generations of stars, being transformed and enriched each time through stellar processing happening repeatedly. The cosmic recyclers are stars, and dust is what they recycle endlessly, creating the chemical richness that makes our existence possible today on Earth. When we look at galaxies through telescopes, we see stars shining brightly throughout. These stars trace out spiral arms, galactic bars, and central bulges clearly. But stars are not the only component of galaxies at all. Between the stars lies dust, vast amounts of dust spread throughout the galaxy. This dust is largely invisible in visible light because it doesn't glow brightly. But it profoundly affects the galaxy's appearance and behavior in many ways. Dust absorbs starlight, passing through the galactic disk from stars behind it. This absorption creates dark lanes and patches visible in images of galaxies. Our Milky Way galaxy has a prominent dark lane running along its length. This dark lane is dust, concentrated in the galactic midplane, absorbing background starlight. The dust makes the galaxy appear darker in those regions than it actually is. Without dust, the galaxy would appear uniformly bright without dark features present. The dust doesn't just absorb light, but also scatters it in different directions. Blue light is scattered more strongly than red light by dust grains present. This preferential scattering makes objects behind dust appear redder than they actually are. Called reddening by astronomers studying these effects carefully observed in data. Distant stars seen through dust appear red, even if they're intrinsically blue stars. This reddening tells us about dust along the line of sight toward them. The distribution of dust traces the galaxy's spiral arm structure beautifully when observed. Spiral arms contain more dust than the regions between arms do typically. This is because spiral arms are density waves that compress gas and dust. The compression triggers star formation in the arms, creating bright young stars. But it also concentrates dust, making the arms appear dark on one side and bright on the other side where new stars have formed recently. Dust also outlines regions of active star formation throughout the galaxy clearly seen. Wherever new stars are forming, there's a concentration of dust present nearby. Because stars form from collapsing dust clouds, as we've discussed earlier in detail, the dust marks the birthplaces of stars even before the stars become visible. By mapping dust, we map where star formation is happening currently today. This helps us understand how galaxies grow and evolve over cosmic time. In infrared light, dust doesn't absorb but instead glows brightly throughout the galaxy. The dust absorbs starlight in visible wavelengths, heating up from that absorption, then re-radiates this energy in infrared wavelengths we can detect with telescopes. Infrared images of galaxies look completely different from visible light images taken. The dark lanes in visible light become bright lanes in infrared light, completely reversed. This is because we're seeing the warm dust glowing instead of starlight absorbed. The total amount of dust in a galaxy is substantial and significant overall. Milky Way contains about 100 million solar masses of dust total. That's about 1% of the total mass in stars throughout the galaxy. It seems small, but this dust has enormous effects on the galaxy's behavior. It cools gas, allowing star formation to occur in molecular clouds efficiently. It provides the raw material for forming planets around every new star. And it regulates how galaxies appear to observers based on viewing angle. Galaxies seen edge-on show prominent dust lanes cutting across their midplanes clearly. Our own Milky Way would look like this if viewed from outside the galaxy. Galaxies seen face-on show spiral arms with dust tracing the inner edges, where the spiral density wave compresses material into the arm effectively happening. The viewing angle dramatically changes how much dust we see and where. This can make the same galaxy look very different from different perspectives viewed. Dust also affects how we measure distances to galaxies and their properties. Because dust absorbs and reddens starlight passing through it, significantly present. Stars behind dust appear dimmer and redder than they actually are intrinsically. If we don't correct for dust absorption, we underestimate the galaxy's luminosity and overestimate its distance because it appears dimmer than it should be. Dust corrections are essential for accurate measurements of galaxy properties taken today. In starburst galaxies, where star formation is extremely rapid and intense currently, dust can be so abundant it completely obscures the galaxy in visible light. These ultra-luminous infrared galaxies are invisible in visible light, almost completely dark, but glow incredibly brightly in infrared from warm dust radiating powerfully throughout. The dust absorbs nearly all ultraviolet and visible light from young stars, making the galaxy appear as a bright infrared source without visible counterpart present. The dust distribution in galaxies also tells us about the galaxy's history over time. Galaxies with lots of dust are actively forming stars currently today observed. Galaxies with little dust have exhausted their gas and stopped forming stars. The dust content reflects how much raw material remains for future star formation, and how active the galaxy has been in the recent cosmic past time. Dust can be transported around galaxies by various processes happening continuously throughout. Stellar winds from massive stars blow dust away from star-forming regions outward. Supernova explosions accelerate dust to high velocities, spreading it through the galaxy. Galactic fountains carry dust above and below the disk in vertical flows. Then it rains back down onto the disk, later enriched with new elements. This circulation of dust through the galaxy mixes material and enriches it. The dust also interacts with the galaxy's magnetic field present throughout space. Dust grains with magnetic properties align themselves with the field lines present. This alignment affects how dust scatters light, creating polarization patterns observable. By measuring polarization, we can map the galaxy's magnetic field structure indirectly. The dust acts as a tracer, revealing the invisible magnetic field geometry. Dust in the dark is the hidden skeleton around which galaxies organize themselves. It's invisible in most wavelengths, but crucial for understanding galactic structure overall. The dust traces star formation, absorbs and re-radiates energy, affects measurements made, and reveals the galaxy's history and future potential for making new stars. Without dust, galaxies would be simpler, less interesting objects to study completely. The dust adds complexity, beauty, and insight into how galaxies actually work. It's the hidden component that astronomers must always account for and study, to fully understand the galaxies they observe throughout the universe today. Everything on Earth ultimately came from interstellar dust floating in space originally. This might sound poetic, but it's literally true in the most scientific sense. Every atom in your body was once part of a dust grain drifting through the galaxy billions of years ago, before our sun even existed. The connection between you and cosmic dust is direct and profound completely. Let's trace that connection from dust to life step by step carefully. Our solar system formed 4.6 billion years ago from a collapsing cloud. That cloud contained gas and dust from previous generations of stars, as described. The dust grains were made of elements created by those earlier stars' fusion: silicon, carbon, oxygen, iron, and dozens of other elements in combination together. These dust grains contained the raw materials needed to build planets and life. Without them, Earth couldn't have formed with the properties it has today. As the solar system formed, dust accumulated into planetesimals and then embryos, eventually colliding and merging to form the rocky planets, including Earth created. Every atom in Earth came from those original dust grains in the cloud. The iron core in Earth's center was once iron dust in space. The silicon and oxygen in rocks was once silicate dust grains floating freely. The carbon that would later become essential for life was carbon dust, all compressed together by gravity into a planet-sized ball over millions of years. Early Earth was a molten ball of rock without a solid surface anywhere. As it cooled, the surface solidified into a crust of rock material. That rock contained silicon, oxygen, magnesium, aluminum, iron, and other elements derived from cosmic dust that had formed the planet originally at the beginning. The oceans formed from water delivered by comets and asteroids impacting Earth. Those comets and asteroids were also made from cosmic dust and ice. From the outer solar system, where ice remained solid during formation time. The water molecules in the ocean contain hydrogen and oxygen atoms specifically. The hydrogen is primordial from the Big Bang, originally at the start. But the oxygen was made in stars through fusion reactions during their lifetimes, scattered into space by supernovae and incorporated into dust grains drifting there. Those dust grains eventually became part of the water on Earth's surface. The water that would become essential for life to emerge and thrive. The atmosphere formed from gases released by volcanic activity on early Earth. Carbon dioxide, nitrogen, water vapor, and other gases filled the early atmosphere. These gases came from the planet's interior, where they were trapped originally, in the dust and rock that formed Earth in the first place. The nitrogen you breathe was once part of dust grains in space, incorporated into Earth during formation and later released as gas into atmosphere. Life emerged in Earth's oceans about 4 billion years ago, approximately estimated. The first living organisms were simple cells without any complex structures inside. But even these simple cells required complex chemistry to function and reproduce. They needed carbon to build organic molecules, forming their structures completely. Hydrogen, oxygen, nitrogen, phosphorus, sulfur, and many other elements working together. Every one of these elements came from cosmic dust ultimately and originally. The carbon in all organic molecules came from carbon dust grains initially. That carbon was made in stars through helium fusion burning in their cores, released into space when those stars died and scattered their enriched material. The carbon became part of dust grains that later formed Earth and atmosphere, eventually incorporated into the first living cells through chemical reactions occurring. Every carbon atom in your body followed this exact path through stars, from fusion to dust to Earth to life to you today. The same is true for every other element in your body without exception. The calcium in your bones was made in stars and scattered as dust. The iron in your blood was forged in supernovae and became dust grains. The phosphorus in your DNA was made in dying stars and became dust. Every element heavier than helium followed the path from stars to dust, then from dust to Earth, and finally from Earth into living organisms. You are literally made of stardust in the most direct scientific sense possible. But it's not just the elements themselves, but also their arrangement that matters. Life requires very specific chemical compounds like proteins and DNA to function. These complex molecules could never form inside stars where temperatures are extreme. They can only form in the cool environments of planets like Earth, where liquid water provides a medium for chemistry to occur in solutions. The dust delivered elements to Earth, where conditions allowed complex chemistry developing, creating the molecular building blocks of life through gradual chemical evolution happening. The dust also delivered organic molecules directly to Earth in some cases. Scientists have found amino acids and other organic compounds in meteorites landing. These organics formed on dust grains, in space, or inside asteroids forming. They were delivered to Earth, ready-made rather than forming here originally. This might have jump-started life by providing crucial building blocks already formed, making the origin of life easier than starting from simple elements alone. Water itself is crucial for life, and also came from dust grains. Water ice formed on dust grains in the cold outer solar system regions. These icy dust grains accumulated into comets and icy asteroids that formed. Later, some of these objects fell to Earth, delivering their water to surface. The water you drink contains hydrogen and oxygen that was once ice. On dust grains, billions of years ago, drifting through space silently there. The nitrogen in your proteins and DNA came from nitrogen dust molecules. Nitrogen is made in stars and released into space through stellar winds. It forms nitrogen molecules that freeze onto dust grains in cold clouds. These dust grains brought nitrogen to Earth, where it became part of atmosphere. Eventually incorporated into living organisms through biological nitrogen fixation occurring. Every breath you take contains nitrogen atoms from ancient cosmic dust. Life has flourished on Earth for 4 billion years continuously since beginning, evolving from simple cells into the incredible diversity we see today. Plants, animals, fungi, bacteria, all sharing the same chemical basis for life. All using the same elements delivered by cosmic dust billions of years ago. The entire biosphere is built from recycled stardust delivered by dust grains. Every forest, every ocean, every creature is made of former dust. Human beings are the universe becoming aware of itself through evolution. We are cosmic dust that has organized itself into conscious, thinking beings. The atoms in your brain were once scattered across light years of space. Now they're arranged in patterns that can contemplate their own cosmic origins. You are a way for the universe to know itself, as Carl Sagan said, made possible by the cosmic recycling of dust through stars and planets. When you look at the night sky, you're not separate from it. You're part of it, intimately connected through every atom in your body. The dust drifting between stars is your distant ancestor in a literal sense. The elements in your body have been recycled through multiple stars potentially, each one adding to the chemical richness that makes you possible today. You are a temporary arrangement of cosmic dust that can think and wonder about its place in the vast universe from which it came ultimately. Most dust remains within the galaxy where it formed throughout its entire existence, circling the galactic center in endless orbits, drifting through molecular clouds slowly, participating in cycles of star formation and destruction repeatedly over billions of years. The dust becomes part of stars, planets, and potentially life within its home galaxy. But some dust grains escape from their galaxies entirely and become cosmic wanderers. These grains journey through intergalactic space for unimaginable distances and timescales continuously. Their journey represents the ultimate cosmic voyage that any particle can possibly undertake. From one galaxy to another, across millions of light years of nearly perfect emptiness. Several powerful mechanisms can eject dust from galaxies into intergalactic space effectively today. Supernova explosions are among the most violent and powerful ejection mechanisms available naturally. When a massive star exhausts its nuclear fuel and collapses catastrophically inward, the resulting explosion releases more energy in seconds than our sun produces. In its entire 10 billion year lifetime, combined together as radiation and kinetic energy. The shock wave from this explosion accelerates surrounding material to tremendous velocities instantly. Some dust grains in the vicinity get caught in this shock wave and accelerated rapidly, reaching speeds of thousands of kilometers per second from the explosion's tremendous force. At these incredible velocities, dust can exceed the galaxy's escape velocity completely. Instead of eventually falling back down into the galactic disk under gravity's pull, the dust continues outward forever, escaping into the intergalactic space surrounding the galaxy. Stellar winds from massive hot stars provide another mechanism for dust ejection continuously. These luminous blue supergiants and Wolf-Rayet stars emit powerful streams of particles. Charged particles flowing away from their surfaces at speeds reaching thousands of kilometers per second. The stellar wind exerts continuous radiation pressure on dust grains near the star. Over extended time periods, this persistent pressure can accelerate dust grains outward gradually. Particularly effective if the star is located in the galaxy's outer regions already, where the gravitational binding energy is weaker than in the dense central regions. The dust gets pushed outward bit by bit until it reaches escape velocity. Then continues outward into intergalactic space freed from the galaxy's gravitational grasp. Active galactic nuclei, powered by supermassive black holes, create the most powerful outflows. These AGN-driven winds can reach velocities of 10,000 kilometers per second easily. When material falls toward the supermassive black hole at the galaxy's center rapidly, it releases tremendous gravitational energy that heats the surrounding gas to extreme temperatures. Some of this hot gas gets channeled into powerful jets shooting outward along the black hole's rotation axis at nearly the speed of light incredibly. Other material gets blown outward in broad winds expanding in all directions. These outflows carry enormous amounts of gas and dust away from the galactic center, sweeping through the galaxy and out into the surrounding intergalactic medium beyond boundaries. AGN-driven winds are particularly effective at ejecting material because they originate deep within the galaxy's gravitational potential well, where binding energy is strongest throughout. Galaxy collisions and mergers provide another dramatic mechanism for dust ejection happening. When two galaxies approach each other and their gravitational fields begin to interact, the tidal forces created during the interaction are violent and chaotic completely. Each galaxy raises tides on the other, pulling material outward into long streamers. These tidal tails contain stars, gas clouds, and substantial amounts of dust particles, pulled from the main bodies of both galaxies during their gravitational dance together. Some of this material remains gravitationally bound and eventually falls back into one. Of the merging galaxies as they combine over hundreds of millions of years. But a significant fraction escapes from both galaxies into intergalactic space permanently, remaining as orphaned clouds drifting through the space between galaxy groups forever after. These tidal debris clouds contain dust that was formed inside galaxies originally, but now wanders homeless through intergalactic space, disconnected from any galaxy's gravitational embrace completely. Once dust escapes into intergalactic space, it encounters a fundamentally different environment entirely. Intergalactic space is extraordinarily empty compared to even the emptiest regions inside galaxies. The average density in intergalactic space is about 1 atom per cubic meter. For comparison, the interstellar medium within galaxies contains thousands to millions of atoms per cubic meter depending on location within the galaxy structure throughout space. This million-fold decrease in density means dust grains in intergalactic space almost never collide with gas atoms or other dust grains during their entire journey ahead. They drift in essentially perfect isolation through the cosmic void surrounding galaxies. With no gas to provide drag forces, no nearby stars to heat them up, no magnetic fields to guide their motion along field lines, as happens inside galaxies. Just the incredibly faint cosmic microwave background radiation providing minimal warmth throughout space. The temperature of intergalactic dust is extremely cold in these isolated conditions. Only about 2.7 degrees above absolute zero from the microwave background alone. This is the same temperature as the cosmic microwave background radiation itself everywhere. At this frigid temperature, any ice mantles coating dust grains remain frozen indefinitely. The grains don't evaporate or sublimate away into gas over time passing by. Their chemical composition remains stable and unchanging during the intergalactic journey happening. They become preserved in almost perfect stasis like cosmic time capsules sealed shut, carrying information about their galaxy of origin forward through space and time together. The dust grains record the chemical composition of stars in their home galaxy. The isotopic ratios created by those stars' nuclear fusion reactions in their cores. The organic molecules that formed on grain surfaces in dense molecular clouds. All this information remains frozen and preserved during the long journey through emptiness. The journey through intergalactic space takes an incredibly long time to complete anywhere. Even traveling at several thousand kilometers per second from the initial ejection event. It takes millions of years to cross even the relatively small gaps present between galaxies in groups or clusters where galaxies are closer together gravitationally. The local group containing the Milky Way and Andromeda spans about 10 million light years. Dust traveling at 1,000 kilometers per second would take 10 billion years approximately. To cross this distance from one side to the other completely traversing it. To cross the much larger voids between galaxy clusters could take hundreds of billions of years. Far longer than the current age of the entire universe, which stands at 13.8 billion years since the Big Bang occurred initially at the beginning. This means most wandering dust grains are still in transit through intergalactic space. having not reached any destination yet since their ejection long ago from galaxies. During this extraordinarily long journey spanning eons of cosmic time, continuously forward, the dust grains are exposed to cosmic radiation from all directions throughout space. High-energy particles called cosmic rays, mostly protons and atomic nuclei traveling at nearly light speed, constantly bombard the dust grains from every direction randomly throughout. Ultraviolet and X-ray photons from distant quasars and active galactic nuclei also strike the dust grains regularly, though these sources are extremely distant and faint. This radiation slowly damages the dust grain structure over very long timescales gradually, breaking chemical bonds in molecules, coating the grain surfaces through photodissociation happening, sputtering individual atoms from the grain surface through energetic particle impacts occurring, gradually eroding the grain size through this constant bombardment over billions of years, over extremely long timescales spanning tens of billions of years of exposure time. This radiation erosion could significantly alter or even completely destroy dust grains, reducing them back to their constituent atoms, dispersed into intergalactic space forever lost. Though the extremely low density of intergalactic space means erosion proceeds very slowly, much slower than inside galaxies, where radiation fields are millions of times stronger. Some intergalactic dust grains eventually encounter another galaxy during their wandering journey, as they approach the new galaxy following their trajectory through space ahead. The galaxy's gravitational field begins to pull on them from vast distances away, accelerating the dust inward toward the galaxy from their original trajectory path. The dust enters the galaxy's dark matter halo first, an extended diffuse region, surrounding the visible galaxy, containing most of the galaxy's total mass in invisible form. Then the dust continues falling inward through the hot gas in the galactic halo. This halo gas is heated to millions of degrees by gravitational compression and shocks. But it's extremely diffuse, so the dust passes through without significant heating occurring. Eventually, the dust reaches the galaxy's disk, where most visible matter concentrates today, where stars orbit and molecular clouds form from dense gas accumulating over time. The dust settles into this disk, joining the existing dust population there already. When wandering dust enters a new galaxy from intergalactic space beyond boundaries, it brings unique chemical information and history with it from its origin elsewhere. The dust's elemental composition reflects the types of stars and supernovae that existed. In its home galaxy at the time, the dust formed originally billions of years ago. These chemical signatures can be measurably different from the native dust in the new galaxy, because different galaxies have different star formation histories, creating different chemical evolution. Large galaxies have undergone more stellar generations and are more enriched with heavy elements. Small galaxies have undergone fewer stellar generations and remain less chemically evolved overall. Dust from a large enriched galaxy entering a smaller, less enriched galaxy would stand out compositionally from the native dust through careful spectroscopic analysis conducted today, creating slight variations in the chemical composition of different regions within galaxies observed. By studying these compositional variations carefully in detail, astronomers can trace the history of dust mixing between galaxies through these intergalactic transfer processes occurring throughout time. The dust also brings distinctive isotopic signatures that serve as fingerprints of its stellar origin. Different types of stars produce different isotopic ratios in the elements they create. Through the specific nuclear reactions occurring in their cores under varying conditions present, supernovae create different isotope ratios than asymptotic giant branch stars do in their processes. Supernovae produce lots of silicon-28 relative to silicon-29 and silicon-30 isotopes created, while AGB stars produce more silicon-30 from neutron capture reactions in their interiors. By measuring isotopic ratios in dust grains using mass spectrometry techniques available today, we can determine what types of stars created those specific grains billions of years ago. Even after the grains have traveled across intergalactic space and entered new galaxies, the isotopic fingerprints survive and tell us about ancient stellar populations that created them. This makes dust grains cosmic archaeologists carrying information about stellar nucleosynthesis, from galaxies far away in both space and time back to earlier cosmic epochs. Some wandering dust might carry complex organic molecules formed in its home galaxy. Carbon-based molecules like polycyclic aromatic hydrocarbons that formed on dust grain surfaces, or in the gas phase within molecular clouds where organic chemistry proceeds actively. These organic compounds could survive the journey through intergalactic space remarkably well, protected by ice mantles coating the grain surfaces that shield them from radiation, or simply because the radiation field in intergalactic space is so weak comparatively. When the dust eventually enters a new galaxy and participates in star formation there, these organic molecules could be incorporated into protoplanetary disks around newly forming stars, and eventually into planets and comets forming within those disks over time, potentially seeding those new planetary systems with pre-formed organic chemistry delivered from another galaxy entirely across intergalactic distances spanning millions of light years of space. This raises the scientifically fascinating possibility of panspermia operating between galaxies hypothetically. If complex organic molecules can successfully travel between galaxies on dust grain carriers, could the building blocks of life, or even life itself, somehow be transferred between galaxies through this mechanism operating over cosmic timescales throughout the universe's history? This remains highly speculative and faces numerous challenges to overcome successfully working. The harsh radiation environment would likely destroy any biological molecules during the journey. The timescales involved are so long that any biological structures would decay completely. But it represents an intriguing theoretical possibility for the spread of life's chemical precursors across cosmic scales far larger than previously imagined by astrobiologists studying life's origins. Perhaps the organic chemistry that led to life on Earth was partially seeded by dust grains that originated in another galaxy billions of years ago and wandered here, carrying with them the chemical legacy of stellar populations from a distant cosmic island. The population of dust existing in intergalactic space is extremely difficult to observe directly, because the dust is so incredibly dispersed throughout the vast intergalactic volumes. And because it's so extremely cold, at just a few degrees above absolute zero, the dust emits very faintly only in the far infrared wavelengths where its thermal emission peaks, according to blackbody radiation laws, at these frigid temperatures maintained throughout. Our Earth's atmosphere completely blocks far infrared observations from the ground, unfortunately, requiring space-based telescopes to detect this faint emission from intergalactic dust present. Space telescopes like Spitzer and Herschel have detected faint infrared emission signals from dust in intergalactic space between galaxies, confirming its presence there definitively. But measuring its detailed properties, composition, and total abundance remains extremely challenging. With current technology and instruments available to astronomers today studying these regions, computer simulations of galaxy evolution now include intergalactic dust in their sophisticated models. These simulations track how dust gets created inside galaxies by stellar processes, how it gets ejected from galaxies through the various mechanisms discussed earlier above, where it ends up in the intergalactic medium surrounding galaxy groups and clusters, and how it might eventually be reaccreted back into galaxies through infill processes. The simulations suggest that a significant fraction of all dust ever created by stars eventually ends up in intergalactic space rather than remaining in galaxies permanently bound. Some models predict that intergalactic dust could contain as much total mass as all the dust currently residing within galaxies throughout the observable universe today, representing a major previously overlooked component of the universe's total dust budget overall. Though observational confirmation of these theoretical predictions remains difficult with current capabilities. The wandering dust grains are truly the universe's nomads traveling the longest journeys. Each individual grain has a unique and remarkable history stretching back billions of years. It formed inside a star in one particular galaxy long ago at some point, through nuclear fusion, creating heavy elements that condensed into solid particles afterward. It was ejected violently into space through a supernova explosion or stellar wind, accelerated to tremendous velocity, and flung out of its home galaxy entirely forever. It has been traveling ever since through the near-perfect vacuum of intergalactic space, perhaps for billions of years already, without encountering anything substantial along the way. Perhaps it will eventually reach another galaxy and participate in forming new stars there, continuing its journey through the cosmic cycle of creation and destruction that drives the universe's evolution toward ever greater chemical complexity over time passing forward. Or perhaps it will wander forever through the empty spaces between galaxy clusters, never reaching anywhere in particular, just drifting eternally through the expanding universe. As cosmic expansion carries it farther from all galaxies over time, accelerating outward, these wandering grains connect galaxies together in ways we're only beginning to understand fully. They transfer material and chemical information across cosmic scales, previously thought completely isolated. They enrich intergalactic space with heavy elements that would otherwise remain locked forever in the galaxies where those elements formed originally through stellar nucleosynthesis occurring. They represent the universe's fundamental tendency toward mixing and homogenization over long enough times, where initially separate and isolated systems gradually become connected through these subtle, exchange processes operating on timescales of billions of years throughout cosmic history elapsed. The universe is not a collection of isolated island galaxies, as it might appear superficially, but rather an interconnected web where material flows between galaxies constantly, though slowly, building invisible bridges between cosmic structures across the ocean of intergalactic space existing. Some of the dust wandering through intergalactic space today might eventually return home, surprisingly, in galaxy clusters where dozens to thousands of galaxies are bound together gravitationally and interact frequently through close passages and occasional collisions occurring over time. Dust ejected from one galaxy might later fall into another galaxy in the same cluster. That second galaxy might later undergo its own ejection event, sending dust outward again, some of which might eventually fall back into the original galaxy billions of years later, creating a circulation and recycling of dust throughout the entire galaxy cluster over time. This recycling on cluster scales gradually mixes and homogenizes the chemical composition of all galaxies within the cluster over many billions of years of exchange happening, each galaxy contributing dust to and receiving dust from all the other cluster members, creating a shared chemical heritage throughout the galaxy cluster group over cosmic time. The journey of wandering dust represents the ultimate expression of cosmic recycling happening, starting inside stars, where elements are forged through nuclear fusion burning fuel, escaping from galaxies through violent ejection mechanisms into the surrounding space beyond, traveling through intergalactic space for potentially billions of years in isolation silently, eventually perhaps entering new galaxies where the entire stellar cycle begins again from scratch. These grains have seen more of the universe than almost anything else existing anywhere. They've traveled farther through space and longer through time than any human spacecraft will ever conceivably travel, even with our most optimistic future technological projections considered. They are the true explorers of the cosmos, silent witnesses to cosmic history unfolding, carrying their secrets and stories through the vast empty spaces where few things venture. The wanderers connect the universe together, one microscopic dust grain at a time, building invisible threads of material connection between galaxies across the cosmic web's large structure. They prove conclusively that nothing in the universe is truly isolated or alone completely. Everything is connected through these patient cosmic journeys, happening continuously throughout time. Material flows between all structures on timescales long enough for exchange to occur. The universe is one interconnected system, despite the vast distances separating its components. And dust is the messenger carrying material and information between distant parts of this cosmic whole, weaving together the fabric of the universe through its wandering journeys ongoing. The story of cosmic dust is not a simple linear narrative from beginning to end. It's not a tale with a clear starting point and a final conclusion somewhere. Instead, it's a cycle that repeats endlessly throughout all of cosmic time without stopping. Dust forms through stellar processes, transforms through various mechanisms, builds complex structures over time, and eventually returns to its starting point to begin the entire cycle again. This eternal cycling is like breathing in a profound and beautiful way metaphorically, with the universe inhaling and exhaling matter slowly and rhythmically throughout its existence. over timescales spanning billions of years from the start of one breath to its completion. Each cycle enriches the universe slightly more than the previous cycle did before, creating ever-increasing complexity and chemical diversity with each repetition happening through time. This is the fundamental rhythm underlying all of cosmic evolution we observe today. The cycle begins with stars creating dust through fusion reactions and explosive deaths. As we've discussed extensively in earlier sections, stars forge heavy elements in their cores. Through nuclear fusion reactions, converting hydrogen into helium, helium into carbon and oxygen, carbon and oxygen into even heavier elements like neon, magnesium, silicon, and iron progressively. These fusion reactions release the energy that makes stars shine brightly across the cosmos. But they also create the chemical elements essential for making solid dust particles. When stars exhaust their nuclear fuel and reach the end of their lifetimes, they expel their outer layers into space through various mechanisms depending on mass. Low-mass stars like our Sun become red giants and blow off their envelopes gradually, creating beautiful planetary nebulae with shells of gas expanding outward into space. Massive stars explode catastrophically as supernovae, violently ejecting their outer layers instantly. Both processes scatter newly created elements into the surrounding interstellar medium thoroughly. The hot gas from these stellar deaths contains all the heavy elements created during the star's lifetime, plus additional elements created during the death process itself. This hot gas expands and gradually cools down over thousands of years of expansion time. As it cools below certain critical temperatures, atoms begin sticking together, chemically bonding, forming the first solid particles that we call dust grains condensing from the gas. This is the creative phase where new dust is born from stellar deaths happening, adding fresh material to the cosmic dust reservoir that accumulates slowly over cosmic time. The newly formed dust drifts outward from the stellar death site into interstellar space, joining the existing population of older dust from previous stellar generations that came before. This mixing of new and old dust gradually homogenizes the chemical composition throughout space, making the elemental abundances more uniform as different sources contribute their unique material. The mixing happens through turbulent motions in the interstellar gas carrying dust along, and through diffusion as dust grains randomly walk through space over millions of years. Eventually, this mixed dust accumulates in giant molecular clouds where gravity pulls it together. These clouds are the gathering places where dust from across large regions of the galaxy comes together in high concentrations far exceeding the average interstellar density present elsewhere. The clouds can contain millions of solar masses of gas and dust combined together, spread over regions hundreds of light years across in three-dimensional space extending outward. These clouds are cold and dark inside with temperatures just 10 degrees above absolute zero. The dust shields the cloud interior from starlight, creating darkness essential for what follows. In the molecular clouds, dust plays its crucial role in enabling new stars to form. By cooling the gas through efficient thermal emission of absorbed energy into space, by shielding the gas from ionizing ultraviolet radiation that would heat and disrupt it, by providing surfaces where hydrogen atoms can meet and form molecular hydrogen gas, Molecular hydrogen is essential for star formation, but can't form efficiently in pure gas. The dust grain surfaces catalyze this reaction, making molecular clouds possible to exist. Without dust, the clouds would be too warm and too ionized to collapse under gravity. Dust makes star formation possible through these multiple essential roles it plays simultaneously. New stars form from the dust-enriched clouds through gravitational collapse of dense cores. These collapsing cores fragment into multiple pieces that each become separate stars eventually. The dust goes along with the gas as everything collapses inward together, concentrating into protostellar disks where planets will eventually form from the material accumulating there. This is the constructive phase where dust actively builds new structures from itself, creating the next generation of stars and planetary systems through gravitational assembly processes. Planets form from the dust in protoplanetary disks through very gradual accumulation over time. Starting from microscopic dust grains, just microns across initially, as discussed earlier extensively, growing to millimeter-sized pebbles through gentle collisions, sticking particles together slowly. Then to kilometer-sized planetesimals through continued accumulation, sweeping up smaller particles. Finally, to planet-sized bodies through gravitational interactions and giant impact collisions occurring. This planet formation process takes several million years to complete from start to finish. Some of the dust becomes incorporated into rocky terrestrial planets like Earth and Mars. Some gets incorporated into the icy cores of giant planets like Jupiter and Saturn. Some remains in smaller bodies like asteroids and comets orbiting throughout the system. And some get secreted onto the central star during its formation, feeding its growth. The dust has now been transformed from free-floating interstellar grains into gravitationally bound structures. Solid worlds held together by their own gravity, persisting for billions of years stably. The transformation from diffuse dust to solid planets represents an enormous increase in organization. From disordered particles to ordered structures with differentiated interiors and complex geology. On some of these newly formed planets, conditions become favorable for life to emerge eventually. The planet needs to orbit at the right distance from its star where temperatures allow. Liquid water to exist on the surface as a solvent for biochemistry to operate. The planet needs sufficient gravity to retain an atmosphere protecting the surface below. It needs the right chemical elements in sufficient abundance for complex chemistry developing. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and many others in proper amounts. All these elements came from the dust that formed the planet, originally from the disk. The dust provided every atom that makes up the planet, its atmosphere, oceans, and life. Life represents the highest expression of dust's potential for creating ordered complexity shown. Dust organized into incredibly complex patterns that can grow, reproduce, and evolve over time, maintaining themselves against the universe's tendency toward increasing disorder and entropy spreading. Life is dust that has learned to temporarily maintain organization through metabolism and reproduction, creating ever more complex forms through biological evolution operating over geological timescales. From simple single-celled organisms to complex multicellular life to intelligent conscious beings. all built from the same cosmic dust that once drifted through interstellar space billions of years ago. But even life, with all its remarkable complexity, is temporary in the cosmic scheme. Eventually, the planet's host star will exhaust its nuclear fuel and reach the end of its main sequence lifetime after billions of years of stable hydrogen fusion burning. When our sun becomes a red giant, approximately 5 billion years from now projected, it will expand enormously in size, its outer layers reaching beyond Earth's current orbit. The inner planets, including Earth, will likely be engulfed by the expanding sun, vaporized back into hot gas from the extreme temperatures experienced inside the star's atmosphere. The planet's solid matter will be disassociated back into individual atoms and ions floating. All the dust that once formed Earth will be returned to gaseous form completely. All the structures that dust had built over billions of years, the mountains and oceans, the atmosphere and biosphere, every living thing that ever existed on the planet's surface, will be vaporized and returned to space as the star sheds its outer layers, creating a planetary nebula that expands outward, carrying this material away from the dying star. This is the return phase, where complex structures get broken down and everything reverts to being dust and gas again, floating freely through space, waiting for the next cycle. The dust expelled from the dying star joins the general interstellar medium once more thoroughly, mixing with dust from other dying stars and from supernova explosions, enriching it further. This recycled dust is now even more chemically enriched with heavy elements than before, because it has passed through another complete generation of stellar nucleosynthesis, adding to its composition. The iron from Earth's core formed inside an even earlier generation of stars previously, has now been through at least 3 complete stellar cycles of processing and enrichment. Each cycle increases the abundance of heavy elements like carbon, nitrogen, oxygen, and iron, making the universe progressively more chemically complex over time as cycles continue. The first stars that formed in the early universe contained almost no heavy elements, just hydrogen and helium from the Big Bang with trace amounts of lithium present. But after 13 billion years of stellar cycling and chemical enrichment occurring repeatedly, the universe now has substantial amounts of every element up to uranium and beyond, all created by stars and scattered through space in dust form repeatedly over time. The recycled dust then participates in forming the next generation of stars somewhere nearby, drifting into new molecular clouds that form from the enriched interstellar medium present, collapsing under gravity to form new stars that will live, create more dust and die. And the entire cycle repeats with those new stars going through their complete lifetimes. Some of that new generation's dust will form planets around those stars potentially. Those planets might harbor life if conditions are suitable for biochemistry to operate. Eventually, those planets will be destroyed when their host stars die as well, inevitably, returning all their material to dust once again to begin the cycle anew completely. This repetition has been operating for over 13 billion years already since stars first formed, and will continue operating for trillions of years into the future as long as stars exist. The cycle is not perfectly closed. Some material escapes into intergalactic space permanently, As we discussed in the previous section about wandering dust grains traveling far, this represents a slow leakage of material from galaxies into the intergalactic medium surrounding. But the amount lost is relatively small compared to the total dust cycling within galaxies. Most dust remains trapped within its home galaxy, cycling through stars repeatedly over time. Each galaxy operates as its own semi-closed recycling system, processing dust through generations, creating an increasingly enriched chemical reservoir over cosmic history as cycles.